Cool. Oh yeah. Thank you for coming, guys. I know it's kind of early, 11 a.m., and apologize for being slightly late. But welcome to a robot learning reading group here in Toronto that I'm hosting. First of all, I want to thank Bracketbot for sponsoring some of the snacks and the drinks. So if you don't know about Bracketbot, these are what they look like. They're sort of like these two wheels, self-balancing. And they recently added arms to them, or they're working on adding arms to them. And the idea is it's a really cheap open source robotics dev kit. So the robot arms nowadays, they're very expensive. It's really hard to get into robotics because hardware is expensive. They're trying to make it more accessible. So if you're interested in getting a kit, you can sign up to a wait list because they're still working on improving the Bracketbot. So thank you to Bracketbot for sponsoring today. And I'll do a quick intro about who I am. My name is Steven. I currently study at Waterloo. I spent the summer working on robot learning at Dyna Robotics. They're a startup in California, and they also work on general purpose robots. And previously, I also did some software internships at Tesla and NVIDIA. And some cool things about me, I have a website, stevengong.co, where I host a bunch of notes. And so if you're curious about like the things I'm thinking about or what I'm learning, you can go there. And then I also have a small YouTube channel that I work from time to time. And I've been working in robotics for a long time. Been very interested in, at first I was doing a lot of like autonomous vehicles, but now I'm doing more like robot arm and manipulation. And today, we're hosting this reading group to sort of discuss the Pi 0 and Pi 0.5 paper. And I'm gonna do it, so I did one in Waterloo and did a lot more talking, and I realized I should ask more questions in between to make it more interactive, because I assume like everyone has read and we're here to sort of discuss the paper. And so I think like generally when I read a paper, these are sort of the questions that we should try and answer. So first of all, like let's try to understand what is the objective of the paper, right? And we should also discuss what was done prior to this paper, what are the limits of the current approach, what is new about this Pi 0 paper, how are they evaluating this model, and then what are some limitations that they mention and that they don't mention. So we're going to try to answer that today. Do you think there's any other questions that we should think about as we discuss this paper that I'm not discussing?
There are many questions, but I think I'll ask again.
Okay. All right.
I think how this paper is different from this company, Figure.ai.
Figure, okay.
They had partnership with OpenAI, but now they have their own one. So lots of like small questions.
Okay, yeah, we can discuss that. Yeah, so Pi 0, right? I linked to this website because they had this blog where they showcased the paper. And so this model that they trained is they claim it, they say it's their first generalist policy, and you can see it can do a lot of really cool tasks. I think some of the videos are here, and I guess my Wi-Fi is a bit laggy. But yeah, like putting eggs in the carton, folding t-shirts, folding towels, stacking bowls, a bunch of different tasks. So at the end of this, yeah, these are sort of like the things that I can do. It's a pretty general purpose robot foundation model. So I guess we can jump straight into the paper and discuss different components. And I will stop so we can discuss these different parts. So number one, before even we talk about the model architecture, they talk about their dataset training mixture. So you'll notice in robotics, there's sort of like you can train it on one robot, or you can train it on multiple robots. And you see a lot of these robot foundation models, what they'll do is they'll train on multiple embodiments. So Pi 0 is one of these examples. Like if you look at some older robot foundation models like RT1, RT2, RT1X from Google, they also train on multiple robots. And so these are sort of like the robots they use, the UR5, the Franka, and the Bamanuwa URX, so different embodiments. And the idea...
When you say multiple robots, do you mean like simulations or like actual controls?
Actual, like physically, like, so what they'll do is they'll have a bunch of people, like they call them operators, and then they'll have some sort of setup. There could also be simulation data, right? But yet, why it's different embodiment is like each of these robots are controlled differently, right? So, for example, a single arm setup versus a double arm or bimanual setup, it's 7 motors or 6 motors versus 14 motors, right? So the way you control these robots are very different, and the interface through which you control these robots are different. There's many like different details that each of these robots, like they might be controlled differently, or like one is like joint controlled, the other is like some other representation of how you control the actions. But I would say, like, why do people train cross-embodiment, right? Because at the end of the day, when we deploy these models, they'll be for a specific robot, right? Either you deploy on a Franka or Euro 5. And generally, you always need to fine-tune, which means you need to collect more specific data for that robot. Because imagine, like, I collect data folding a t-shirt, and I deploy it. How does the robot, like, I deploy it on a robot. If you just have a pre-trained model, it's been trained like on a bunch of robots, you don't really know, like, okay, what am I supposed to do? Like, which robot is it? Because each robot has its own action representation. Does this make sense so far? Any questions on this cross-embodiment training?
So these are different form factors of robotics, and then you're training one model which can work across different form factors?
Right, yeah. And the idea is, like, why would you do this, right?
Why would you do this?
Yeah, the idea is, the argument is that if you force a model to like sort of work across all these embodiments, you will have a more capable model that can generalize better, right? So like this model needs to work on a Euro 5 and also a Franka, and it sort of needs to learn some representation that can like solve both like for a Franka and a like Euro 5, or like different embodiments, and so it can help with its generalization capabilities. Is the argument, right? It definitely does worse. Like imagine you train something specific for one robot versus one that will work across all robots. I think like, at first it might work better for I think performance-wise, the model that's trained on one robot will work better, but it might not be as generalizable as the one that's been trained on multiple robots. But this is still an open research problem. So some companies will only train on one robot, and some companies will just like do cross-embodiment training. But right now, the trend in the field seems to be cross-embodiment training.
Okay. Because the pattern which I remember was training specialized robots. So if you look at a company like Covariant, they train a lot of models, but they just do one thing at once.
Yeah, like Figure only has one robot.
That's the unique part of it.
Yeah, Optimus has like, all these humanoid companies only have one robot, and they'll just collect. But yeah, like Pi and some of these general purpose robotics companies will try to train on multiple embodiments. Yeah, and so in terms of where you get this data set, OXE is the one from Google. It's very, they did this in like 2022. But these are all just like different robotics data sets. So you get like an image, and you have the joint measurements. And then they also mentioned internet pre-training. So this actually doesn't, this just comes from using a model. So now we can discuss the model architecture if there's no questions on the cross-embodiment training in the data mixture. But essentially you just like get robotics data set.
What do you mean by pre-training? So like, so Pi data set makes sense. It's a robotics data set.
Yeah, so pre-training, yeah.
So is it like the robotics data set which is available on internet, or they're actually training on text?
They are not training on text. So the internet pre-training, so good question. It comes from using a pre-trained VLM. And since this VLM is pre-trained, that means this VLM the weights have been trained on the internet, right, the VLM. So that's where it comes from. When they actually do this training, like this architecture, once you load in your pre-trained VLM, you're gonna only use robotics data set. And the thing you learn is the action chunk.
So it's a language model, but a smaller language model, like Gemma.
Yeah, so let's zoom into, so the VLM is PalyGemma. And PalyGemma is just composed of Gemma, the language model, which is trained on just pure text. And then they'll use SIGLIP. So SIGLIP, I have an image here, is something separate that learns to align text and image embedding. So there's a text encoder and an image encoder in CLIP, and you will train this through contrastive loss. And the idea is that you'll align, like if I give you an image of a dog and the word dog, they should exist in a similar space in the latent space. And so, and then contrastive meaning like if it's the same, you'll try to minimize it, and if it's different, you'll try to maximize it. So this is this contrastive loss idea. So once they've trained this clip model separately, they take the image encoder and then use it. And then there's a linear projection, because like this is a different model than this. Like the latent space exists like differently. So there's a linear projection to project these images into the same space as the language model. But that's basically the VLM. It's a language model that's pre-trained. You take a vision encoder that's pre-trained, and you should like slap them on together. And then the linear projection is to sort of like get the vision and the language to align in the same space.
So this vision encoder is trained on image data or video data?
The vision encoder is trained on image text pairs.
Image text pairs.
Yeah. So these are all just like text. There's no like video. But so this is the pre-trained VLM, right? So you can think about it like it has a good vision and language understanding. I would argue it doesn't have a good spatial understanding, right? Because like if you think about how the vision encoder is trained, it's just like trying to align text and image. So there's some techniques like when you mask an image and have your vision encoder or something called mask autoencoders, where you mask patches and then you have an encoder and then a decoder structure to reconstruct the masks. Those probably have like some better spatial understanding because they have to reconstruct these patches. But here, the objective is like a pure contrastive loss where we align the text and the image. I'm going to align the text and image. Does this make sense? Am I going too fast? So yeah, this is a VLM. It's called a VLM because you take image and text, so visual and language. Right? And the thing it outputs in this case of VLM is text. So these are text tokens, right? So a lot of these tasks, so if you look at this example, it's an image, and the text will be like a query, like where is the photographer resting? And then so this VLM needs to predict like a good answer for this, right? So in this case, it's a guy sitting in a hammock. So this is the VLM. It does not output images, it just outputs text tokens. So you take this pre-trained VLM, and so that's how you get your internet pre-training. It has a good visual and language understanding, but now we want to make it work for robotics. So so how do you do this? I guess we can talk about what was done prior, right? If we go back to the questions of like what we're trying to answer, how was it done prior to this work and what were the limits of the current practice? If you look at the first few robots foundation models, what you can do is, or what they did was introduce action tokens. So you wouldn't have an action expert, right? You can imagine you take your VLM and like robots, like there's different actions. You can discretize it into a particular token. And then you can say, okay, this token represents a particular like trajectory. Maybe like moving to the left by 0.1 meter is a particular token. Right? So you have like 256 of these tokens. So if you look at like OpenVLA, that's what they do. The RT1 and RT2 models, they also did that. But that's not what they do here. What they do is they actually introduce a completely separate action expert. And here they work in continuous action space. Any questions so far about what I'm saying?
Can you repeat the RT part? So RT retrained it within the same tokenizer space, I'm assuming?
Yeah, maybe I can pull up an image. RT1. Okay, maybe I'll just pull up my notes. So this is OpenVLA, and then let's do RT1. Okay, and this is the image. So yeah, in RT1, RT1 doesn't even use like a pre-trained VLM, but you have these discrete actions that it outputs. I think maybe the OpenVLA image is a bit easier to understand. OpenVLA, right, it also just uses a VLM. Well, it's a Llama plus some other, Siglip as well, right? The same idea, but they use Llama instead of Gemma. And then they take there's some tokens. So in OpenVLA, the least used 256 tokens will be swapped out with action. And then so you predict in these token space. Does this diagram make sense?
Yeah, so you expand the tokenizer, you retrain with the new tokenizer space.
Yeah.
And then you predict actions and then there's a leak.
Yeah.
What do you mean by action detokenizer?
Action detokenizer, I assume, is like you need to go from a token, like what this token actually represents, and then you just the token is some delta x, delta or position, and then orientation, and then grip, open, pose.
It says that this is my job basically, is a data. So, but you train a new tokenizer or a detokenizer, and let's say the model has seen the vocab of the model is 128,000. Then what you'll do is you'll expand it to all the actions that you can take. Let's say for a computer, it's up, down, left, right. And if you want to do up or go down or left or right, you will add that in the tokenizer.
Okay.
And so the ID, the detokenizer, what they'll do is the model will protect that ID. It passes the detokenizer, and it'll give you the action that the model is supposed to take.
So in LLMs, we are predicting language. Here you are predicting action.
Yeah, actions basically, because the model only sees IDs. The model doesn't know if it's an action or a text. It just knows this particular token is an action token.
Got it.
And so you'll pass that to, based on the ID, you'll pass it to the tokenizer.
Yeah. I'm not sure how, I guess, you expand the token space. I mean, I remember briefly reading this and it was saying like Llama has a like fixed set of like tokens it can support, like number of tokens, and then they'll just like the least used 256 tokens, they'll just like say, okay, we're just these like usually represent some text characters, right? Grouping of text characters. We'll just say, okay, ignore those. Now this ID represents action, and then when they feed in the data set, they'll use like the robot action, they'll tokenize it, they'll say like, oh, it corresponds to this ID, and then this is the ID you should predict.
You can actually override it. So you can override it, but for the most part, it's Hugging Face, all these libraries support adding new tokens.
Okay.
The model hasn't seen them obviously, so what you have to do is basically reinitialize new embeddings in the model, and it's basically it's a standard normalization.
Okay.
And then you have to retrain the model so that it has seen these tokens.
Yeah.
And it's basically an extended pre-training, but with these tokens.
Okay.
And you re-include some of the pre-training data so the model doesn't forget. It's like applicable knowledge. But this is like a standard recipe that people use for basically any domain.
Yeah.
Where you retrain the model with new tokens and then you predict basically just like this.
Okay. Yeah. This discussion is also relevant to the Pi 0.5 paper because what happens is like these large language models, you know, they're used to working in this discrete token space, right? And so now we're going back to Pi 0 and we're saying because robotics, we want to work with continuous action space. And I think like it's kind of hard to make this work together. So you'll see in the Pi 0.5 paper, they actually do their pre-training with discrete action tokens. And then when in their fine-tuning phase, they will like predict a continuous action space through the flow matching step. Because I think language models don't work well with continuous action space. So that's because they work with tokens fundamentally. And any other questions or follow-ups on the architecture? I didn't talk about the action expert yet.
Yeah, that was the question.
Yeah. So one idea would be this action expert. So how do we integrate action? Right before this, there was the Octo paper. So there's this guy called Kevin Black who worked on the Octo stuff, and he actually had this talk that I watched recently motivating sort of like how they came about the Pi 0 architecture. Because I was also like, why don't you, because if you look at the, Octo is another foundation model that I can show you guys. I wouldn't quite call it a robot foundation model, right? But here you see the action expert is just this action head. So you go through the entire transformer forward pass, and you just like take the output of this transformer and then do you slap a multi-layer perception on there and then output action. So that's actually what they tried initially. Right. So if you look at, I guess I can't zoom in, but like what you could do is like you take the output tokens, or like you just use the last layer and then slap on your action head. But here it's sort of like side by side. So actually what's happening, I sort of drew up this diagram, is that within your transformer, right, there's like, in this case with PalyGamma, there's like 18 transformer blocks stacked on top of each other. And you can think that if you only use the very last layer, right, and use the information from the last layer to like initialize, to feed into your action expert, the last layer, because it is sort of like a pretty lossy representation of like, useful information, right? Like, because the last layer, what you're taking the last layer and then you're doing a softmax, right? So the information that's used there is just like so that you have a good like softmax. But they're in between all these layers, there are probably better representations that capture what the image and the text is about. And so what you're going to do is you want to leverage that information. So you're going to add a separate action expert, which is, this action expert is actually just like a smaller version of Gemma, but it's uninitialized. It's not like you're loading some language model weights. It's like from scratch a transformer with 300 million parameters. And then after the end of each transformer block, you're going to do this attention to let information flow from the VLM to the action expert. So if you look at like the attention matrix, it sort of looks like this, where the actions can attend to the image and the text, but it sort of like doesn't flow the other way around. So I guess it limits sort of the information propagation, or like information can propagate through that causal, to this attention mechanism between each layer. And they actually open source this. It's probably easier, if you really want to understand how this works, is to go into the code and see how they do this.
What is this diagram of? Is it I?
Sorry?
What is this diagram of? Is it of the model?
Yeah, of the Pi0 model. Like, this is my drawing, my interpretation of how it's implemented. Right, so like, if you just zoom into like how these two actually talk to each other, it's through this sort of attention mechanism. Yeah, and then what this also enables is that inference time, you actually only need, you can cache sort of like this side of the equation, because like what they'll do is flow matching. They actually need to like do a forward pass of this like 10 times at inference time. And I'll explain flow matching in a second. We can discuss like flow matching, which I think is pretty cool and interesting, which like other papers have not done as much. But to make this actually like work really fast at inference time, they'll make use of KV caching. And then I guess this diagram just shows like what is fed into the inputs. You have your images, you have your text. There's proprioception, which is just like your joint measurement, like joint angles, like the motor measurements. And then the action itself, you actually need to pass in a noise. It's like Gaussian noise. And that's required for flow matching. And at the very end, you get your action. The action is actually a velocity field action. It's not directly like what the robot should do, because you need to integrate this over time. And but it's an action chunk, meaning that because with a lot of these like super large models, like inference takes a very long time. So what you need to do to actually make it somewhat useful is, instead of predicting one action, you'll predict like 32 actions ahead of time. So you query the model once, you run 32 actions, then you query the model again, run 32 actions, as opposed to query the model once, run one action, query the model, run one action. So that's a very common technique that's used with these robot foundation models. Yeah, any questions?
Just a question. So at every step, so let's say you go through VLM layer 1, you're also querying the action model, and then you're getting
they sort of run side by side.
Side by side. Right?
Yeah.
Because first when I saw the diagram on the previous slide, I assumed that once
it's not like it goes like this. It's not like that. It's sort of like it really runs in parallel. And that's, I think, was confusing at first, is like why they put the diagram side by side.
I've seen this diagram a lot more, so that makes sense to me.
Yeah, and so yeah, I was trying to explain why they do that is because you sort of like want to leverage the representations between these layers, as opposed to just like at the very end. And yeah, that was like also what they argue. I think this is quite like clever and interesting, because you see a lot of other papers. Yeah, they'll just like finish the full forward pass. Oh, did I lose my connection? Carol, I lost my connection. No more connection. No more connection.
Oh, it disconnected.
J'ai perdu ma connexion, ouais. Womp womp.
You turned off? Give it a sec. 1 sec. Not sure. It's trying its best. Yeah, there you go.
Cool, thank you. Yeah. Yes, I think it was quite clever that they do this sort of like side by side as opposed to doing a full forward pass of the VLM and then feeding that into the
I
action.
don't understand the math. I think I need to go deeper into it.
Yeah.
But so I'm just accepting as a mathematical operation. I'm doing like SID lecture, so
Yeah.
I get that part.
Yeah, I think I also sort of like it's yeah. The way I sort of like understood this better is just like writing out the shapes. Like, what is the output shape of the VLM? What is the output shape of the action expert? So, and then looking at sort of how a transform works in between and then how basically they do a concatenation of the tokens and then do the attention and then split the tokens back, or like split the context length back. So so the VLM has like a certain like number of tokens. Let's say L. Like let's say L1 and then action expert is L2. They actually have a different hidden dimension for the VLM has like 2048 hidden dimension and then action expert has like 1024 hidden dimension. And I was like, how does that work if they have different hidden dimensions? But it's like when you do the attention and then you multiply by your WQ, WK, W weight matrices, then the head dimensions are aligned. And then you can, because like when you do attention, you actually do like multi-head attention. So then each head, the head dimension is the same for all of these.
Yeah,
and then
partition the head space.
Yeah. Yeah.
Oh, okay, that makes sense.
Yeah, and then you make sure the head dimensions are the same for both the VLM and the action expert. And then you sort of like concatenate.
Heads.
Yeah, because then you just have like I think, yeah, I also can get lost with this.
The way you're describing is effectively the attention dimension is 24.
2048.
Last time 24. So like 3072, right?
Yeah, you're probably a bit more knowledgeable about transformers. I mean, I was just trying to, like this is like how I visualize it mentally, or like you have like L by D, or initially you have your embedding matrix. Or okay, this is like looking at how a transformer works. Like, this is like my way of so you have your tokens, you have IDs, you have an embedding matrix, get your input embedding, get a positional encoding, then it's L by D, right? So each of these is a particular like embedding, right? It represents a word or like a token, and then layer norm, and then once you're here, you like split it into QKV, and then you multiply by WQ, WK, WV, and the sort of dimension you get is L by D, right? Because it's L by D times D by D. So this D doesn't have to be the same D, like it's another D, and this is like where you align it, right? So if it's like L by 2048, multiply by 2048 by some other number. If it's 1024, it'd be 1024 by some other number. But then after this multiplication, this Q, K, and V are sort of like the same values for both the VLM layer and the attention or the action expert. And you split it into heads, and then when you do the multiplication, L by dk times dk by L, that gives you your L by L. So when we're visualizing the
That's actually quite smart.
when we're visualizing this, yeah, that's your L by L. But so you can I think where did they concatenate it? I believe here.
Multi-head, right? So the next step, once you have it, is you put these back together.
Yeah.
And so, for example, you have like 2048 plus 1072,
1024, yeah.
1024. So what will happen is that the first set of heads will go back into 2048.
Yeah.
The latter heads will combine to 1024.
Yeah.
And so you'll just jointly train basically on both, and you'll still have the attention heads in both of those models.
Okay.
They combine. When you concatenate, they go back into their place. So
Yeah.
you basically reconstruct the dimension once after multi-head attention.
Yeah.
And so it makes actually sense. I've never seen this before. So this is
Yeah.
interesting.
Yeah. This is, I know it can get kind of confusing. I would say like if you, go ahead.
No, it's all good.
Yeah, I think like if you want to look at the implementation, you can go OpenPy and then source models. They have a PyTorch and a JAX implementation now, or like a PyTorch implementation now. They used to only have JAX implementation, and then Py0 here, and then you can sort of see It's either in PyZero, PyTorch or Polygemma PyTorch, and then they call it like prefix. So the prefix refers to the tokens for the VLM, and then the suffix refers to the tokens for the action. And then there's like the attention mask, I believe, or there's like different masks that you need to work with, and then Polygemma with expert. You forward this, and I believe it is here. Yeah, I think somewhere in this logic, there's a concatenation, compute layer complete. I think after you compute layer complete, yeah, I think here, right? So you query, you concatenate here. So there's inputs and embeds. There's like these are, yeah, you have your image, your text, your proprio, and your action noise. You do sort of this compute QKV for all of them, and then you concatenate here. And then somewhere after you split it, yeah, we can, yeah, I don't want to spend too much time on this, but I think this is very interesting. Okay. Any questions on this stuff that you want to talk about architecture-wise?
Is it a general architecture for all robotics model, or this is unique here?
Like this idea, I think, is very unique to PyZero. I think like, yeah, I listed, if you look at our event page, our Luma, I listed a bunch of other robot foundation models. And like the ones recently that came, I mean, there's not that many open source, like good robot foundation models. The other one, there's like Groot, which is like, it doesn't use flow matching, it uses diffusion. And it's also conditioned, I believe, on, it's not like conditioned like this. Like it also uses a VLM, but it's like closer to the last layer.
Architectural elements, like if I say across all the robotics model?
A VLM, they'll use a VLM and then attach some way of getting action out of it, adding an action head. That's a very common architecture. And the VLM generally is pre-trained on, yeah, internet, like image text pairs, so that it has a good like image understanding. Yeah, that's I'd say like the most common idea. And then flow matching. Okay, I don't want to spend too much time on flow matching, but I can explain sort of how it works. Has anyone like know what flow matching is, or someone wants to like explain this actually? Oh, okay. In robotics, what I'll say is why it's needed is robotics like has sort of like this. A lot of times you have these tasks and you end up like it's pretty multimodal in the sense of like there are two modes of a distribution, not like modality as in like image versus text, but like literally your distributions will look multimodal. So in this case, this task of pushing, this is called the push T task. And here what we're trying to do is push the gray T box into the green T box. And you can see that we sort of like have these two modes. You can either go around to the left or go around to the right, right? And if you just naively do this, right, you sort of just end up learning the mean of these two, because if you use something like, yeah, regression, you're just gonna regress to the mean, right? And in which case you're just gonna like try to go down the middle. But really you want to capture this multimodal distribution, right? Like in video generation or image generation, you have like, it's also pretty multimodal. In this case, yeah, the trajectories can be very multimodal. And so you want to be able to capture this. And so flow matching is very similar to, or like the idea is built on top of diffusion. I was asking myself like why they do flow matching instead of diffusion. And the best answer that I have right now is like, it just training wise, it's like easier, right? Than diffusion. Yeah, well, your training is one step, and then at inference time you do multi-step. But like diffusion training is also, you have like multi-step, right? Because you're just starting from noise and then you slowly, or you learn slowly, like you have your original image, slowly add noise, and then you learn how to denoise that across multiple steps. And then inference time, you just do this Flow matching is at training time, what you learn is sort of this velocity field. So the way this diagram is sort of my mental model of how it works. You start from noise, and you want to get towards this multimodal distribution. So this is like a 2D visualization. And so the easiest way to do this is learning sort of like I guess you can imagine a river, and you start from a random position, and you need to get to some position. And so you sort of like, you let the flow of the river pull you towards your destination. So you're learning this velocity field. And so, do I have some math here? Yeah, the loss is here. So what the model predicts is a velocity field, and the ground truth is just the difference between your noise and the ground truth action. So you learn the velocity field, and this is constant. So whether you're at this point, at this point, at this point, the velocity field is the same. And so you sort of like, so you sample noise, and then you have where you need to get to. That's a velocity field. And then you sort of like sample points in between along this velocity field. So your model is conditioned on these points, and learn that at this point, the velocity field should be going to that direction. And so you can imagine if at inference, you only did one step, it would collapse down to the mean. But because you do this multi-step thing, you let your velocity field pull you towards the modes. So at first, maybe it might go down the middle, right? But hopefully the thing you learn is this multimodal distribution, and you get pulled towards your modes. That's sort of like a very abstract way of explaining this. I think there's a lot of work by Meta on flow matching. There's like some guides. But yeah, this is sort of my understanding of flow matching. You need the 10-step inference as opposed to one-step inference, because if you just do one step, you suffer from the same problem of just learning the mean, or like going towards the mean of the modes, as opposed to actually going to the modes. So yeah, the inference, this is the equation, right? So this is what I described. You start from noise, and you slowly integrate your action with the velocity field. And the delta that they use is 0.1, so that they do it 10 times. So you start from from tau equals 0 to tau equals 1. Okay, and that is essentially how they get the action, right? So they train this action expert, right? The action expert, so the way it looks, like how do we integrate flow matching with this is like the ground truth action that it learns is this velocity field, right? So the model predicts this velocity, and then you'll use this model at inference time. You'll do like 10 forward passes. So you start from Gaussian noise, you do one pass, okay, and then you take that number, and then do that same process again 10 times until you get to your final point, and that's the actual ground truth action that is going to be used to control your robot.
One question.
Yeah.
What is the cycle time?
The latency, you mean?
Because in robotics, cycle time is very important. Robots
Yes.
are taking action in real time. So
Yeah. So because they can, if you don't leverage KV caching, it's very, very slow. But because you leverage KV caching, there's a lot of most of the computation comes from the action expert. Because, so if you think about like, you refeed the action always keeps changing, but the image is always the same, right? Like the image and the text is pretty much fixed. So you don't need to do computation on the image and text side, but on the action side you do. And so they actually get like, if you look at their claimed inference times, it's around 70 to 80 milliseconds, which is, I would say, actually really good. You also execute action chunks. You don't execute one action. There's even more work that needs to be done that they don't mention in this paper, right? Because you can imagine what happens is you have your model, query your model, run an action chunk. And then you query your model. While you're querying your model, your robot is not running, right? So it ends up like being very jittery if you just do this naively. So there's also work that needs to be done you can, while the robot is moving, query your model again. They talked about how they tried this. In this paper, I think they tried it and it didn't work as well. But they have like other papers like real-time chunking, which talks about this idea of like overlaying, like while your robot is running, how do you like query your model again? And actually what they'll do is they'll condition the model on like what the robot is currently doing. And they'll try to like solve for a trajectory that is consistent with the previous, like what the robot is currently doing. Any questions so far?
When you mentioned action chunks, is it like partial actions?
What do you mean by partial?
Is it just predicting one action, or you said action chunks?
Yeah,
Like
it's multiple actions, yeah.
multiple actions.
Yeah, an action chunk is multiple actions. So 16 actions specifically in this paper. Yeah, I guess it could, you would think maybe an action chunk is like a subset of the action as opposed to multiple actions, right? Okay, yeah. The action chunk idea came from the action chunking with transformers paper. I guess to give you guys an intuition of why action chunking works or is useful, is also you can think of it as like, let's say your task takes 100 time steps to complete, right? So if your model every time you predict only one time step, and you sort of like do this auto-regressively, right? Because like the model is just like, I do something, okay, and now I'm here, and I do something, and now I'm here, right? You can end up like having these compounding errors. I believe I have a diagram here, yeah, of like how I visualize it, right? Like if the ground truth is this, and you query your model auto-regressively, you can, it's like the error compounds, right? As you get more and more out of distribution. Now think about it, if you did action chunking, all right, let's say I used an action chunk of 10. Then that means I only need to query my model 10 times as opposed to 100 times. So you reduce the effect of the compounding errors, right? So like you ideally, like, it's sort of like hand waving, but yeah, the intuition is like because you query your model less, you have less chance to, you don't run into as much compounding error. So you essentially reduced the horizon of your problem from 100 to 10 from the perspective of the model. And so that's why it's been so effective. Yeah. Any questions on the action chunking stuff or anything I've talked about so far? Okay. And I guess how it, out of the box, I guess these are some results. Zero shot, okay, versus, yeah, I think, I don't remember why I put this, but overall I think the model does pretty good. I think like somewhere between like 50 to 60% in some of these tasks. And when you fine tune, right, when you fine tune is you collect smaller amounts of data with specific to a particular robot. Although I think here actually sometimes they were fine tuning with multiple robots. Actually, I'm not super clear on this, but generally when you fine tune is you collect higher, I think, yeah, fine tuning could refer to collecting data for a specific task, specific robot, but more generally I think when they refer to fine tuning is they look more carefully at the data, right? Like higher quality data, whereas in the pre-training, because you're just like giving it so much data, you have less care in terms of like what the data is actually doing. Maybe you would have a question like, how do you define high quality data in robotics? That is also an open-ended question. I think we're at a point now where we are starting to get the scale, right? Like we have, all these companies have like operators, they collect data, right? And you can see like Pi, even at Dyna this summer, like we're able to have pretty general purpose or like robust models. Or like they can complete the task. It's a few years ago, if you just asked it to do t-shirt, no matter what you do, like it just doesn't work. We're at a point now where it can do some of these tasks, but I think the axes of scaling is not super duper clear. Like when you were in the LLM space, data quality is still kind of important, right? Like they, you want to make sure that the quality, the data sets like Wikipedia, like they're very high quality. So now for robotics, like how do you define a high quality robotics data set is still an open-ended question. Because if you just scale up, the amount of robotics data, it doesn't work super well. Like in the text setting, right? Like if you feed gibberish to the model will output gibberish. It will learn to speak gibberish, right? Same idea for robotics. Like if you just like do random things, like with the robot arms, like because it's imitation learning, it's treating this data as ground truth, right? it's just going to imitate the way the robot behaves, right? So that's why, yeah, a lot of operators, there's like guides on like, you want to make sure you do these very smooth and controlled movements as opposed to like doing like very jittery movements. But I think it's still an open-ended question of like, what more do we need to scale on? And I think right now it's like, okay, it can fold a t-shirt, but when it's in a failure mode, right, like when it fails, it doesn't know how to recover from it. And so what some people do is like you just collect recovery data, right? But that feels like a very, like it's a lot of like human resources dedicated to just like teaching the robot to recover from failure modes. And it doesn't enable the model, like if we want these general purpose robust models, like what do we need to do, right? Like, so there's some open-ended ideas. Perhaps RL can help this a lot, right? Because in RL, you let your model run and you let the model sort of self-improve, right? Because like current paradigm, imitation learning is human experts show you how to do it, you just copy them. But if you go out there in the real world and like, shit, I don't know how to do it, or like the model doesn't really understand what it's just like trying to like do, oh, what would a human do here, right? Because it's just doing imitation learning. And so RL could help with this. The model learns on policy from its own demonstrations. There's also, so yeah, that's what I'm talking about here, better robustness and better generalization. And context learning is also a pretty cool idea. So you imagine instead of fine tuning, you can just show the robot what you want it to do. And then instead of having to re-update the weights, because it has this ability to just learn in context. So actually Gemini Robotics came out with some papers recently, and it's like very good, I think. And then they just basically do in-context learning. Yeah, okay. So those are the open-ended questions, and I wanted to go back here so we make sure we fully answer these things that we want to think about when reading the paper. But did you have a question?
Has anybody tried RLVR? Because I think he organized a meetup on RLVR.
RLVR?
Yeah.
Yeah, that'd be good. We're 500 words.
In like robotics?
Yeah, I saw there was an RL thing here.
5 to 5.
Sorry?
Studio 5 to 5, yeah.
Okay.
Yeah, we were organizing like we're a 500 word lecture, but
Yeah.
I haven't seen that in robotics, like where you have a 1 or 0 signal. But maybe you can code that, I think.
Yeah, it's like there's some work in, sparse signal or dense. I think dense words is more easy to learn, but you can like learn in local optimal, right? In robotics, like, are you familiar with like offline RL? That's like a big line of work. Because like you can imagine, if for those of you who are not super familiar with offline RL, like, right, like if I give you a data set and you do imitation learning, you're just going to treat everything as ground truth. But if you can do offline RL, you basically learn how good a particular demonstration is. And so you can learn that a demonstration is suboptimal because you're learning a value function. You learn like, if like I give you 2 different demonstrations, one takes 2 seconds, one takes 10 seconds, the 2 seconds is way better because you get to your reward much faster, right? So the other one is considered suboptimal. But I guess it's still very difficult. Like we don't know how to scale offline RL. For these long horizons, like learning value functions is pretty hard sometimes, right? Like in these long horizons, especially like with sparse words. So it's, I have some interest in this, and I worked on some of this over the summer. So I'm definitely, there's also like goal conditioned offline RL, where you condition on like goal images to get like your value function is not just like taking state, but it's also taking a goal state is like how close are you to your goal state. And then there's a lot of cool work in that line.
One more question. So is the inference is all local here? We are not going to cloud.
Yeah.
And the model
it runs on an RTX 50 or 4090.
So it's running locally?
So generally the setup in robotics is you have like a powerful station, and then it talks over Ethernet to the robot. Like on board the robot, there's some like controller that runs at a much higher frequency, like 1,000 hertz, that does the low level control. But yeah, you can see it runs on a 4090. Yeah, and then network latency, 13 milliseconds. Yeah. Yeah. Okay. Are there any questions so far? Okay, yeah, so going back to these questions, and maybe you guys can jump in and let's think about this. Like, what do you guys think was new in this approach, and why do you think sort of what they're doing compared to what has been tried in the past? Do you think that will be successful? Like, do you think this is the way, or like? And also, I guess we can talk about like what are some limitations with the current approach that they're not talking about?
Have they